Hi everyone. My name is Victoriya Kalmanovich. I'm a software engineering manager at Predictive, Walmart site here in Israel. And today, we're not going to talk about the coolest Python library or the perfect machine learning algorithm that's going to make you all rich. Today, I'm going to talk about a concept I think is amazing and is going to change the world, and hopefully by the end of my talk, you'll all feel the same. Before I came to Predictive, I served as a software engineer and engineering manager in various roles in the Israeli Navy. I was a lieutenant commander, and in my last role, I was a software group lead. And my story begins about 4 years ago when I was a software group lead in the Navy. One morning, one of my friends I worked with comes in for a coffee break. As a part of his day-to-day job as a project manager in the Navy, he also sails on our vessels from time to time. He has his designated role on the ship. We get to talking about a ship he was on the previous week, and he says that from the minute he onboarded the ship, he couldn't perform his duties because there was a noise coming in from one of the engines that bothered him. He said he had to find the source of the noise and see if there's a failure in one of the engines using only his ears, basically. I joked around, saying, "It sounds like you need an app that listens to the engines and identifies faults instead of you." We both laughed for a couple of minutes, but then we looked at each other and said, "We need an app that listens to the engines and lets us know if they have health issues." Now, when it comes to software projects or apps, I've got the experience I need. This project was different. I had to dive in matters like maintenance and engines and mechanics and whatnot. Clearly, when I started working on this project, I had nothing to do with engines and machines and maintenance. As a first step, I went to research this field called maintenance. I knew my car's maintenance routine, so I started there. Every mechanical piece requires at least 2 types of maintenance. When I take my car, for example, I know that every 20,000 kilometers I need to go to the shop. So I drive it to the shop and say goodbye to my car for a few hours. And during these couple of hours, the guys at the shop go over a set of actions listed on their charts. They clean the brakes or take a look at the engine, and they basically try to prevent faults from happening. At the end of the day, when I come back, I expect my car to be in hopefully a better shape. That's called preventive maintenance, defining regular maintenance periods in advance. This is meant to prevent any failure. But we all remember this one time we missed the really important meeting because the car broke down. That is in case we still remember driving to physical meetings, of course. But anyway, when a car breaks down, that's where breakdown maintenance comes in handy. Breakdown maintenance means we need to find a fix for the fault that has occurred. When it comes to cars, it's not the end of the world. I mean, we'll miss a couple of meetings, or we'll have to take a bus for a week, maybe even rent a car. But when it comes to ships, it's not as simple as that. A ship has missions it needs to perform. We tell other ships to perform its missions for it while it's broken. And what if the ship needs spare parts? What if there aren't any spare parts within the country? We need to order them from abroad and pray they won't get stuck on the way. Once they actually arrive, we need to grab technicians from their current work and tell them to work on this broken piece instead. As you can see, it's a whole mess. So preventive maintenance doesn't prevent all types of faults, and breakdown maintenance is just the worst case scenario. Isn't there anything in between the two? Glad you asked. There is this magical approach called predictive maintenance. You might have guessed it, this approach means we try to predict the failure before it occurs. That's how the world got to researching the field of predictive maintenance, trying to predict the fault before it happens. Like many amazing breakthroughs, NASA was the first to use predictive maintenance as well. Back in the early 90s, a group of mechanical engineers sat around a table and argued they weren't doing maintenance sufficiently enough. They were losing money. This one engineer at the back of the table raised his hand and said he had an idea. So they took 100 engines for the first predictive maintenance experiment and started collecting some data. They discovered that out of those 100 that were supposed to go on their scheduled treatment, only 4 actually needed attending to. So inefficient, right? How did NASA do it? NASA's predictive maintenance of that time was based on a mechanical engineering approach. The approach says, know everything there is to know about the engine. Know how it's supposed to vibrate. Know how hot or cold it's supposed to be at any given moment. And be aware of every other behavior it's supposed to have. Mechanical engineering approach is the classical physics approach. It establishes the behavior of each engine and defines the proper mechanical and movement equations. It designs the set of rules. There isn't just one way to do it. We need to collect data in order to test this behavior, right? And data collection can be done in many ways and from many types of sensors. We can get temperature samples, or oil samples, or vibration analysis samples, and many other methods. For vibration analysis, for example, we know we're looking for anomalies way past the defined rule for maximum vibrations. For oil analysis, we're looking for oil contamination above the defined threshold, and so on and so forth. We have rules that tells us what the data means. This also means, in this case of my project, that I had to have a mechanical engineer leading the way every step of the way, which got me thinking, why not use machine learning? I'd still need a mechanical engineering domain expert to explain the data well, but the change here is that this time the actual data will tell us how the engine is doing and when it's predicted to fail. As the physical approach is rule-based algorithms, I wanted to justify to myself that this machine learning direction I was taking was the right path. I took the face recognition case study as a metaphor to my engine's project. When we want to teach the computer to make a distinction between two people, we know it's not simple, but we could probably work really, really hard and create a set of rules that's accurate enough to make this distinction, right? What about distinction between 3 people? What about 100 people? It gets a little more difficult to do it using rule-based algorithms. Going back to our ship, as vessels advance, the set of rules we must follow grows. Maybe in the past, you could have created models that were good enough. But today, ships are huge. They have hundreds of software, hardware, and mechanical systems on them. Thousands of mechanical pieces. And if that's not enough, we have a bunch of people just running around. Creating a rule-based algorithm in that hectic ecosystem is not so easy anymore. Lucky for us, the world is definitely going in the way of predictive maintenance using data science. So I had plenty of reading material, and I knew where I had to begin. Fortunately for my MVP, I had point number 1, all the sensors I needed already installed on the ship. I also knew, as point number 3 says, I need my data to be time series data. This is very important since the question I was trying to answer was, how long does this engine have until it's going to fail? But point number 2, where was I going to find actual machine data? It's not like I can scrape actual engine's data off the web, right? I couldn't really use our real data, as there wasn't enough of it at the time. Lucky for me, NASA has a very good data set full of machines data that's very well organized and has been collected for over 30 years. And it's public, and it's built for predictive maintenance purposes. This was a great starting point. Next was to actually work on calculating the RUL, the engine's remaining useful lifetime. I needed the alert to be, your engine's going to die in 3 hours, or your engine's going to break in 7 hours. The goal of these 3 next steps is to reduce the error between the actual remaining useful lifetime and the predicted remaining useful lifetime. Point number 1, we started experimenting with data models. Bottom line is there is a big difference between the questions we asked ourselves. Is this engine faulty? Differs from how faulty is this engine, or when is this engine going to break? And each question requires different recordings and different data processing. What is the most suitable approach for a predictive maintenance model? You need to start by understanding which types of failures you are trying to model, which types of outputs you would like the model to give, and what kind of data is available. For us, our problem sounded like a straightforward regression problem, since we're trying to predict something that isn't from a previously classified group. This is often the case when dealing with data collected from sensors. Point number 2, feature engineering. Feature engineering is trying to find the features that are most predictive. Finding the right features was hard for us, but eventually we've come to the conclusion that temperature and maximum vibrations reduce our error in calculating the remaining useful lifetime. And finally, point number 3 is hyperparameter optimization, which I will not go into today. As you can see, we've collected data, chose a model, optimized, just like you do for all data science projects. But there are a few things you need to keep in mind when it comes specifically to predictive maintenance. A dataset for predictive maintenance can face a big problem of class imbalance, where you have plenty of data for working and healthy engine data, and a lot less, much less data on faulty engines or unhealthy engines. This is just like click prediction problems. A lot of people don't press the ad. A lot less people do actually press it. And this makes sense. I mean, it's not like cars break every day, right? Or we wouldn't have bought them, especially ships. This data imbalance might lead to models with very high accuracy but poor prediction performance in real life. Avoiding class imbalance by acquiring this faulty engine's data is not so simple, right? You can't scrape the web and get faulty engine's data. Cars don't break down all the time. You need actual sensors on the actual engines to collect the data. There are many methods to get this faulty or unhealthy engine's data. For example, fix your car every 40,000 kilometers instead of 20,000 kilometers and gain some extra faulty data. And the accuracy challenge. We all want our models to be as accurate as possible. We measure our accuracy using precision and recall. Precision gives us the ratio between all the predicted faults to all the actual faults. This includes false positives, predicted faults that turned out not being faults. In real life, this means paying more money on maintenance routines than is actually needed. Recall gives us the ratio between all true positives divided by true positives and false negatives. False negatives here means that there was a fault and the system hasn't identified it. When it comes to precision and recall, I can't win them both. In my case, I need to fight for a better recall. I'd rather pay more money for some extra false positives than one false negative, which can mean a failure in the middle of the ocean. To sum up, you go through the pre-processing steps, including feature engineering and hyperparameter optimization. You evaluate your model's accuracy, and this is the part where you decide whether you need to keep on optimizing the results or not. The most important thing for predictive maintenance-based apps is to leave the lab and start testing your model in the real world ASAP. This is more important than trying to get the model to be as accurate as it is. Facing reality here is super critical. When I was a teenager and I used to take my parents' car, I was really scared to get stuck somewhere. So knowing the state of the car and if and when it's going to break would have really calmed me down. Today I don't have to dream. Predictive maintenance is not something of the future. It's happening right now. And I was lucky enough to initiate it for my organization. Now is where you come in. Predictive maintenance is the bridge between the past of the traditional industries, mechanical industries, and the future of AI. I invite you all to do predictive maintenance with me. Let's do machine learning for machines together. Thank you for being with me today. Feel free to reach out.